Podemos ir?
Podemos.
Boa tarde a todos. Em nome da Sociedade Brasileira de Reprodução Humana, eu gostaria de agradecer a todos os presentes por participarem do nosso primeiro webinar de embriologia da nossa Sociedade Brasileira de Reprodução Humana. O título da apresentação de hoje será Selection of Gametes and Embryos Using Non-invasive Methods. Meu nome é Mariana Ribeiro, eu sou coordenadora do laboratório FIV-MED de Campinas, e quem vai dividir comigo a moderação dessa aula é a Thelma Criscuolo, que é coordenadora do laboratório da Clínica Primórdia do Rio de Janeiro. Boa tarde, Thelma, tudo bem?
Boa tarde, Mari, tudo bem, e você?
Tudo ótimo, muito obrigada por ter aceitado o convite em participar dessa aula com a gente.
Obrigada a você pelo convite.
Então, a aula de hoje, quem vai dar essa aula é a doutora Christine Briton Jones. A doutora Christine, ela atua como diretora do laboratório da Reproductive Medicine Associates em New York, a RMA, e como professora associada do Departamento de Endocrinologia e Infertilidade Reprodutiva do Sinai School of Medicine. Ela já trabalhou como pesquisadora e embriologista clínica na Austrália, em Hong Kong, e diretora de laboratórios na Califórnia, Utah, Idaho e Nevada. Ela tem mais de 20 anos de experiência em embriologia clínica e participou do desenvolvimento de técnicas de laboratório que contribuíram para o crescente sucesso das tecnologias de reprodução assistida, com mais de 150 manuscritos e resumos científicos publicados em periódicos internacionais. Ela é palestrante frequente no Congresso Anual da Sociedade Americana de Medicina Reprodutiva, o ASRM, na reunião anual da Sociedade da Costa do Pacífico, o PCRS, e foi palestrante convidada em conferências de fertilidade nos Estados Unidos, Escócia, Inglaterra, Canadá, Austrália, México, China e Hong Kong. A doutora Christine também já foi editora e associada de diversas revistas e periódicos, e hoje ela atua como consultora de embriologia do Conselho Americano de Medicina Reprodutiva Oriental. So, Christine, on behalf of Brazilian Society for Human Reproduction, I'd like to thank you so much for accepting our invitation to the first embryology webinar of our society, and for separating this time from your busy day to be with us today. So, if you are ready, so the floor is yours.
Oh, thank you very much. And thank you very much, Mariana and Thelma too, for thinking of me. I'm so pleased to be asked. Mariana and I worked together for 3 years. I guess it's about 8 years ago now. It's the time's flying by.
10 years, Christine.
10 years, it's even worse.
Yes.
But it's so good to see Mariana's face again, and it's just lovely to be, with the Brazilian people, the few people that I know that I've always enjoyed the company of. So thank you. My pleasure to be here.
Thank you very much, Christine. So now it's your turn.
All right. So I'm going to talk about the selection of gametes and embryos using non-invasive methods. It's not meant to be a comprehensive discussion. This is really just some of the methods and techniques that have been in the literature lately, and I'm hoping that we can have a discussion, have some questions at the end. So let's go ahead. I always start with the disclosures. So I am currently a consultant for Roche Diagnostics. So why is embryo selection so important? I think that the definition of success in assisted reproduction treatment must become a single healthy baby. No longer is it pregnancy rates at all costs, where we've got multiple pregnancies that come into being considered a success. So even twins, because we know that most twin pregnancies are going to be safe. However, even with twins, there's considerable risks to the baby, risks to the mother, and social and other medical consequences as well. So in this period of time, we really should define success as a single healthy baby. But how do we achieve this goal? The way to do this is to transfer a single embryo. However, we want to be doing this without reducing the pregnancy rates that we used to see back in the bad old days of transferring 2 or even 3 embryos. So the non-invasive selection methods in the literature that we'll go through today are ICSI or conventional IVF, IMSI, PICSI, purely looking at the embryo morphology, so the embryo grade, extending culture to the blastocyst, the metabolomics, cell-free DNA in spent culture or blastocentesis. So to start with gamete selection, it's an attractive goal, theoretically, to promote more viable embryos. However, when we think about the eggs, they're a limited resource. So we're going to use all of them. There's no opportunity for selection for the eggs. However, with sperm, we usually we will know somewhere we have the cryptospermic samples where we actually sometimes have more eggs than sperm, but usually we only use a very small fraction of the sperm that's available to us to use. So the sperm is certainly something where we could use a selection tool to help us. So some people have brought up the question, is ICSI going to be more advantageous in terms of getting higher success rates, pregnancy rates than IVF? So generally you will have higher fertilization rates that show that there's no difference in the number of viable blastocysts per zygote. So once you've actually got those ovocytes to fertilize, there's implantation or live birth rates with ICSI or IVF are the same. Because in fact, you actually have some people in our field that think that perhaps the IVF allows, or conventional IVF, allows a sperm selection from natural processes, such as the sperm binding to the egg. But in fact, with all of these over decades now, many studies have shown that once you actually are looking at the fertilized zygote level, that the live birth rates are the same. So now what is IMSI? The acronym stands for intracytoplasmic morphologically selected sperm injection. So the M there is being for morphology. And it uses 100 times objective. So most embryology labs with their ICSI microscopes setups are going to use 40x objective. So this is using 100 times objective. It also requires video camera and magnifiers. And the final magnification that's used is approximately 6,600 times. And you actually have beautiful big figures to see. So here is what we would normally be working under. So the 400 times, I know it certainly is something that I believe that all embryologists do, is to use morphology, use the kinetics of the motility of the sperm to choose the most viable sperm from what we've got available. But this is what we would normally be looking at. So the 400 times, as compared to with the IMSI, with the equipment and the extra expense of the different objectives, but you do get a much higher magnification. And the belief is that you can see ultrastructures within the sperm head that may indicate viability. So the theoretical benefit of using IMSI is a high magnification allows the observation of nuclear or chromatin mass and more detailed ratio of height versus width. So you've got a lot more details. However, and I know this is a very busy slide, but you'll be able to see in the only study that did side-by-side comparison with standard ICSI to IMSI. In fact, what they were doing was couples that had previous failures with 2 failed cycles with normal ICSI, they would then do the IMSI. That's how the IMSI group was formed. But you will see here a lot of non-significance. So you do have a higher, statistically higher fertilization rate, in fact, with ICSI. And then with here, but I suppose the most important part is looking at the ongoing delivery rate, and that was the extra embryos. So here, unfortunately, it was shown that in this study that the IMSI didn't have any advantage over standard ICSI. And so before we actually go on to this one, I think what gets to the nature of why would something, IMSI it's actually quite expensive if you wanted to try this technique. And it seems that it would be a great advantage to get a better look when we're already using morphology as a standard. But I think the problem that underlines this as a tool is that we don't understand yet what is the difference in the sperm that we might be seeing. And I guess an example that, again, we probably are aware of is that we know that even with some, say, a testicular sperm sample that can have very, very abnormal morphology can still actually result in a healthy live birth. So we really still, after all these years, know very little about the correlation of certain sperm or any sperm morphology to outcomes and where the failings may occur with abnormal morphology sperm. The next one, rather than just using morphology, was PIXI. And the P stands for physiological. And to achieve this, there's a thin layer of hyaluron bonded to the ICSI dish. And this is a photograph of the hyaluron and with sperm bound. And the theoretical benefit of using PIXI is that more highly mature sperm will bind to the hyaluron spot on that PIXI dish, and then those are the sperm that you will pick up from the dish. So how do we, with these guys, here we go. So a study by Rapper et al. In 2016 showed that there was no significant differences in fertilization, quality of embryo, implantation, miscarriage, and live birth rates between ICSI and PIXI. The other limitation to PIXI is that it is only suitable for sperm that actually have normal count, normal motility. So the ones that perhaps could really use this technique more, such as your testis samples, actually don't have good enough motility to get the sperm to bind, or bind in good enough numbers to be picking and choosing the ones that you want. So again, I think that to me, the most underlying important thing about the sperm selection is that we still need to study and publish the things that we're seeing, including things that may not work. So that's something that even, again, I keep saying after all these years, but after all these years, we really don't have a good understanding of what might be differences in the sperm. Yet we know that some sperm are definitely more viable than others, apart from when they're not swimming, of course. So if we move on then to embryo selection. Now, the strongest predictor of implantation and live birth failure is chromosomal aneuploidy. And we are all very used to this slide, or maybe even going in reverse. And we've even seen ones that mirror, because the graph showing the percent of embryos which are aneuploid against the age of the egg has a very predictable curve. And so one of the most strongest predictors to say, is this a viable embryo or not, actually is aneuploidy. So one way to select for a higher chance of euploidy is in fact just to grow the embryos to the blastocyst stage. So aneuploidy in day 3 embryos was highly predictive of failure to reach the blastocyst stage. And higher implantation rates with blastocyst transfer compared to cleavage rate transfers is something that we've seen for a long time. We certainly don't believe that growing into the blastocyst stage has any restorative benefit to ploidy or to the implantation potential of the embryos. It's more that the embryos that have aneuploidy can grow quite well up to day 3. So prior to the activation of the new embryonic genome, we don't see much of a difference in the embryo morphology up to that point because it's being governed primarily by maternal genes, maternal transcription. Okay. And another way, another system of selection is actually blastocyst grading. So it's based on the stage of development. The number of cells gives us some information, even though we can't count the cells, but it does for the morphology and the organization of the cells. We can give a grading for that. And the Gardner grading system, which is certainly the most commonly used, uses the blastocyst expansion, and then a grade for the inner cell mass and a grade for the trophectoderm. And this is actually one of our fellows who studied on implantation rates from only euploid embryos in FET cycles, and was over 10,000 embryos, and looked and showed that expansion and trophectoderm grade were not as predictive as the inner cell mass grade. And in some ways, I think now you'll often hear say, well, the blastocyst grading or embryo grading really doesn't afford us any selection. But in fact, so we've shown that when the ploidy status is all euploid, in fact, grade does, and it is shows us statistically significant differences between a B grade and a C grade. So the A's and B grades, so the best quality ones, were actually the same. But it does show that it does show some selection ability. So I think, again, it's something that we've always used and we're always looking for something better. But in fact, just embryo grading is a tool that we've got in our tool belt. So then moving on, so we're still talking about morphology, although we're also talking about the kinetics of the growth of the embryo and time-lapse observation in the embryology laboratory. And here are some of the best well-known, the Geary and so the Eva, with others, and there are others as well. So looking at, in 2014, Werner and colleagues looked at the clinical validation of the Eva system. It was a prospective randomized trial, had 82 patients with 900 embryos, and found that, it gave prognostic designation into 3 different groups. So a low chance of implantation, a high chance of implantation, and there was 5% that they could not assign into one of those 3 groups. However, they found that 45% of the patients had 100% of their embryos were designated in that low prognostic group. And so, in fact, in 45% of their patients, there was no opportunity for selection based on the EVA. And so here it was looking at the usable blast rate with high prognostic and the low prognostic, and sustained implantation rate, which is showing approximately the same. So the take home from this is that they felt that the time-lapse videography wasn't good at predicting ploidy status of the blastocysts. So can time-lapse help distinguish which euploid blastocysts will deliver from those destined to fail? And so this again is, if you think about even in the sort of most successful situation, you have a euploid blastocyst for transfer. We do expect still approximately, 30-35% of them are still going to fail to implant. And then even if they do implant, some are still going to be lost as a biochemical pregnancy. So when we looked at the temporal data, evaluated 5 conventional endpoints throughout the cleavage stage. And adding to that, they looked at additional temporal endpoints from the extended culture. So these were first compaction, the morular formation, first cavitation, blastocyst expansion, and the first contraction. And so here showing of the euploid embryo. So again, this is what's very powerful about this study is that they were only looking at euploid embryos. So with the euploid embryos that failed to deliver compared to those that did deliver, and looking at the time from syngamy to the first cytokinesis, was showing, you can actually clearly see. So there was no predictive power in these additional 5 parameters, which is, it is such a shame, because it would be wonderful if we could have something in the dynamics of the embryo growth that could point us towards within. We've already just established that these all embryos are euploid, but maybe there were some clues into the way that the embryos had grown up to the blastocyst stage. But unfortunately, in this study, they couldn't describe that. I think the metabolomics is something, again, that would be looking at a functional difference between the embryos. And what has been studied is adenosine triphosphate levels in the spent media, glucose metabolism, oxygen consumption. And with all of these, it's very promising, but the technology is lacking. So it's still something that is being performed in research, but really hasn't ever crossed over to being used in the clinical setting. Probably one of the most promising is a relatively new application of PGT, but using, so it's a non-invasive PGT. Oh, I'm sorry, here is the non-invasive and invasive, just comparing the workflow. But the non-invasive PGT is using cell-free DNA that's obtained from the spent culture medium. So here, if we look at to compare the workflow, so non-invasive embryonic DNA sampling, so blastocyst culture conditioned media, or blastocele fluid, if that was the method that was used, will have the media drawn up and put into the PCR tube. Then the trophectoderm biopsy, which we are more familiar with, so where we actually are going to be using a laser to take off 3 to 6 cells of the trophectoderm and so showing here. So those steps are different. You can see this is very simple. So that's something apart from just the non-invasiveness, but from having to staff an embryology lab, it certainly is an attractive thing to think if you could just aspirate up some of the spent culture media rather than the very technically difficult, it takes a long time to train your staff for the trifectodome biopsy, as well as it takes a long time. You're doing each embryo individually, takes a long time to perform. But after that point, the steps are the same. So you're doing the whole genome amplification. Now, the most commonly used, and I would say I think it's commonly used because it's actually being shown to have a lot of advantages, is next generation sequencing. And from there we get our results, and we can then have embryo selection based on aneuploidy or chromosomal aberration. So those are the ones that we would not transfer. Mosaicism, which is of course could be something that we could talk about for hours and hours just on its own, as to whether they would ever be transferred or are put into the same category as aneuploidy, where we would not transfer them. And those that are euploid, and we are happy to select those for transfer. So what is the origin of the cell-free DNA in spent culture media? And it is believed, so the theory is, although it hasn't been definitively demonstrated that this is actually accurate, is that the cells of the embryo undergo apoptosis. So in an animal model, it has been shown that cells from both the inner cell mass and the trifectodome cells do undergo apoptosis. And it's the theory that the cell-free DNA that we see that has leaked from the embryo into the culture media is a result of the apoptosis of those embryos. And so got the cell-free DNA into the media. And again, this is really, again, showing the workflow. So comparing a trifectodome biopsy to the cell-free DNA in the spent culture media, next generation sequencing. And this is a study by Vera Rodriguez in 2018, and was looking at, when you compared the two, what were the results. So in her samples, there was 17 that showed concordance between the two. There was 17 that had partial maternal contamination. And then there was one where the only DNA that was picked up, and this again was in 17 embryos, had full maternal contamination. And then another 5 where they were not able to interpret, so whether there was no amplification or there was a lot of noisy data in the NGS graph, they weren't able to actually make a call on that. Out of those that were concordant between the trifectodome biopsy and the spent culture media, so they found within that 3 were mosaic, 6 were the complementary aneuploidy, a complex aneuploid, or 3 that were the standard, aneuploid. So between the two. Okay. With this is a study by Queenie Young and her colleagues from Hong Kong, just published last year. And it's the largest study that has been used looking at the non-invasive PGT. And here in this top graph, table 4 is comparing her study with 3 recently published ones that you can see, again, have smaller sample sizes, and comparing the sensitivity, the specificity, the positive predictive value, and the negative predictive value. And these all are comparing to the gold standard being the trifectodome biopsy. Okay. And on table 5, so again from the same study, what they did is they looked at, so here is the same numbers. So with a 81% sensitivity, 48% specificity, positive predictive value of 82%, and the negative predictive value of 46%. But when they could exclude for full maternal contamination, so it is 7 embryos that had full maternal contamination in the spent culture media, then the negative predictive value goes up considerably. Okay, and so we would be, I think, fair in assuming that all of those full maternal contaminations would have been euploid. So it certainly would be a risk for calling something euploid for the embryo when you actually don't have the embryonic DNA. And then going further, when they excluded the embryos that were mosaic, so again, the negative predictive value was higher as well. On the non-invasive PGTA, showing that it's the source of the cell-free DNA that can be the problem with this assay. The other thing is the amount of embryonic cell-free DNA. It has been shown to be quite variable. So there are some spent culture media samples that will literally have no embryonic cell-free DNA present. And I've actually put the blastocyst fluid here. And I'm sorry, because I didn't actually put on other slides talking about it. But it was felt that this was, even though it is invasive, so to speak, it certainly is much less invasive than the trophectoderm biopsy. So it's where something similar to, or the exact thing being an ICSI pipette to be put through the trophectoderm cells and into the blastocele and to extract the fluid from the blastocele. And what is interesting, Catherine Rakowski's team has shown that the cell-free DNA, as one might think, just the fact that you're actually going inside the blastocyst should be something more constant and more reliable than the spent culture medium, in fact, was the other way around. So they found that it was highly variable to the amount of cell-free DNA that you would find in the blastocele fluid. So by and large, at least Catherine Rakowski's group, who are certainly active in the research side of this technique, they no longer are pursuing the blastocele fluid. And it's purely on the amount of DNA that they can obtain from that. So commonly the amount is equivalent or less than the DNA concentration of one cell. And certainly when we consider that we used to do PGTA on cleavage stage embryos, one of the big advantages of moving to trophectoderm biopsy was that we were getting 5, 6 cells each time. And so that just made the assay much more robust. So with this non-invasive PGT, we're in a way like going back to what were the limitations of the cleavage stage biopsy in terms of just having one cell. So you're really looking at just the one copy. And so a part of that same puzzle or part of the same equation then is if you've got a very low starting amount of DNA, then you are more vulnerable to errors introduced by the whole genome amplification. And I think everyone knows that the WGA, whole genome amplification, is such a terrific name, but it's actually not the whole genome that is amplified. So there are areas that are amplified preferentially over others, and that's a part of the way that the formation or the folding of the DNA. There are other approaches. Again, I was reading recently papers by Rakowski as I was preparing for this talk, and they're using optimized whole genome amplification, and other approaches are to actually use specific primers for, so it's actually where you will know exactly what parts of the genome that you're amplifying. So this is something that is ongoing and is being improved, basically on like a monthly basis. So it's an exciting time. Okay. Another discussion point about the cell-free DNA is that the what they find is it's often shared, which has been theorized to contribute to variable amplification areas while using the existing PGT platforms. There's evidence of maternal cell-free DNA and the mitochondrial and/or from polar bodies is what they're supposing. This is where the maternal cell-free DNA comes from. And we still really don't know for sure the source of the biological processes that results in the cell-free DNA in spent media. We believe that it is apoptosis of those cells, but there's yet to be a definitive study, certainly in the human embryos. There has been, I believe, one study in a mouse model that actually was a mosaic. So they could kind of look, there was chimeric cells, and that way they could show the cell DNA that they're getting was actually specifically from either the inner cell mass or from the trophectoderm cells. And again, it's leading the way and getting closer to we can say, okay, this is definitely the cells that we're seeing, because a concern could be that perhaps if we have got mosaic embryos and there's different ploidy or colonies of ploidy in those embryos, is it the unhealthy cells that are more likely to undergo apoptosis, and are we then going to be overcalling the aneuploid rate, that perhaps the cells that we would take from trophectoderm might be euploid? And as a way of, I know, up for very hot debate is the idea of correction in embryos. And it could be that if there is such a thing, that it is those aneuploid cells, we don't really have evidence for how within the cell that there could be cytoskeletal ability to pull in and correct the chromosomes, so the ploidy. But we could imagine that the euploid cells could actually be less healthy, therefore they don't divide as rapidly as the embryos that are the euploid ones. And there is some evidence to support that theory in embryonic stem cells, where given a long enough time, if it's been in monosomy, so an embryo that actually had the diagnosis of monosomy and then grown out, that you will actually find that there are some euploid cells. Those euploid cells do divide and do better, at least in vitro. So that's an application that is very artificial as compared to our case for clinical IVF, where we're going to be doing the embryo transfer. So it's not like in the human embryonic stem cells that actually can go on and on and on, I guess infinitely, has many times before it's going to be differentiating, unlike implantation in the human embryo for when we're trying to achieve a pregnancy, because they have a very limited time when they're going to be exposed to the different growth factors and so on, and they have to perform implantation. And so in summary, the development of non-invasive gamete or embryo selection techniques is certainly the holy grail for clinical embryology researchers. There has been paradigm shifts in invasive PGT over the last few years. Genomic techniques advancing and changing on a near daily basis with the use of artificial learning techniques and access to just huge databases. So this is something that, again, leaps and bounds in terms of improving what we can do with our existing trophectoderm biopsies. But these are the things that also are going to be the basis and to be able to help us to improve and perhaps get ready for prime time things like the non-invasive PGT. And my plea to all of you is for reproductive medicine labs to publish their findings on non-invasive gamete and embryo selection, even if there's no positive result. So I believe that's something, and I put down here the Cochrane reviews as a way to remind me of something to talk about. You'll often find when you look at Cochrane reviews in our field that the dialogue will be, there was very few studies with appropriate numbers or controls. Well, we know that that's kind of obvious, because if there is a technique that we feel is beneficial for the patients, it's very difficult for us to then set up a true randomized controlled trial. It's very difficult. If we really do believe that doing even traditional trifectodome biopsy is going to benefit our patients, it's hard to say, okay, we need you to be in this study, you're going to be randomized, you may have that, you may get the trifectodome biopsy, or you might get, say, the biopsy, but we're not going to send it off to the PGT lab. So it becomes very unethical when we're dealing with patients who are trying to, grow their family. And within that, then, my plea is whatever studies you do, publish them. And that's the only way as we're going to be, when we get enough numbers, that we can actually make really good decisions about how ready are these techniques to apply to our patients. And optimization of non-invasive selection capabilities will be the next quantum leap in assisted reproductive medicine. I believe we're so close. Certainly, I think the non-invasive PGT-A is very interesting. We need to understand the source of the cell-free DNA and to continue using the platforms that we're getting to know really well with the trifectodome biopsy, and to improve those. So if we can actually improve the whole genome amplification, and starting with those tiny amounts, this is something that is very likely to become a reality and something that will be very valuable. And I want to say thank you to my colleagues. So this is the embryology team and the fellows. I am so very lucky. I get to work with the REI Fellowship at Mount Sinai School of Medicine. And here on the corner here is Jolie. He's the director of our research. So he keeps these fellows kind of under control. And the physician team. Okay, thank you.
Thank you, Christine. So I think you can stop our presentation view there. Christine, are you hearing me?
Yes, I do.
Okay, so congratulations on your brilliant presentation. So this talk is very interesting, and those techniques are hope for the future, even though they are not proven yet. But what you are saying, we need more studies. We need to try different things, Yeah. So I need to encourage everybody to do that. I totally agree with you. So now, Christine, we're going to start our Q&A section, okay? So Thelma, please, could you start with the first question?
Yes, I have a question. While I'm asking to Christine, if someone watching us at YouTube, you can send us the questions. So Christine, we know that the time-lapse incubators can produce one more blastocyst per patient, but in the sense of choosing the best embryo, is the time-lapse technology effective?
Mm-hmm. So again, I think that the incubator technology with time-lapse actually is excellent. So they're using the very small space. They are able to get their temperature and the gas, so getting the CO2 levels and so on, exactly right very quickly. So they're a wonderful incubator. And of course, brilliant. I love all of the time-lapse videos that they're showing too. So my feeling is that they do show us the morphology grade, which honestly, in my heart of hearts, I believe we can also get just from our standard incubation, looking at the embryo on day 5 or day 6. So, but that is still of value, is the same level of selection that a standard morphology analysis would get if you grow the embryos to day 5. So I think it actually doesn't have any advantage over the static culture conditions, I guess.
Yes.
Yeah.
Yeah, I understood. Okay.
Okay.
And
Are you going to ask something else? Or can I go ahead?
I have another question, but it's our time to play.
No, it's okay. So you can go, Thelma. Go ahead. You're excited.
Christine, I have a question about andrology. Okay. With the advent of the new technologies of seminal selection and processing, do you think that the andrologist profession tends to become extinct?
I know. That's such a good question. In terms of, I think there will be, I think that artificial intelligence is going to come into play in that field, and perhaps in all of our fields, andrology might be the one that it might be of most value and can be so much faster than what we can do by hand. And andrology, manual semen analysis, for example, can actually be quite sort of time consuming in comparing what we do with embryology, where we don't have to be as precise because we're not giving a diagnostic value. I think that the role may change. I don't think that it's going to be taken over completely by the artificial technology. But what I would say to everybody, as like and even people kind of my vintage that have been doing this for many years, we have to be flexible. I would say embrace the technology, embrace the change, learn everything that you can about it and how you can apply it in your labs so that you're not kind of left behind. It's my husband often uses the example of a buggy whip manufacturer when cars came out. And it didn't matter that you might produce the most beautiful buggy whip, but if there's no buggies being sold anymore, you're going to be out of business. So I think we have to, behooves us to learn the technology, embrace the technology, and that way we will be a part of the change.
Yes. So prepare yourself and be the change.
Be the change. That's very good. Yeah.
So I have a question now. So I'd like to talk about the Catherine Rakowski article that was published at PNAS 2019. Okay. So she states that the result of non-invasive PGT is more reliable than compared to trophectodermal biopsy. So due to false positives and negatives of mosaic embryos. So according to this information, Christine, do you think that patients over 40 years old would already have indication for non-invasive PGT, taking into account the fragility of these embryos and the low chance of them to produce new embryos? You know, I'm talking about like, I believe what I have in my lab, like patients over 40 years old, the embryos are more of like fragile, you know. Sometimes we are afraid to touch those embryos. Sometimes the patient has only one embryo and then you have to do the biopsy. So what's your opinion about that?
I think that scenario is going to be the very patient that we hope, once that all of the studies are done and we can be feeling that the NIPGT is going to be reliable, that they're the ones that will benefit for sure. So it's something where we don't have to worry that we might be taking some of the cells. There might not be as many cells in the trophectoderm of a 40-year-old's embryo than compared to, say, a 38-year-old's. However, now I think that it's difficult in that if we aren't sure that we can get the reliable information that first time, what I'm thinking there is we could take the spent culture media, we're going to vitrify the blastocyst. If we don't get a result back, I think that would be my fear, Do we then, we warm the embryo, we're going to then perhaps do the trifectodome biopsy, and then you've got to re-vitrify again, which all of these things you can do, but we expect that it probably does lower the viability of the embryo. So I'm hopeful that soon or in the future, that once we are really confident of that technology, that those are the types of patients that are going to be at an advantage. Right? The first ones. What I think is interesting about the article, so Catherine Mikowski's group, though they're looking at what she believes is that the inner cell mast cells actually undergo a higher rate of apoptosis into the culture media than the trifectodome. So it's almost like doing a CVS compared to an amniocentesis. So she thinks that the cell-free DNA is actually more representative of the inner cell mass than the trifectodome cells, which is interesting. And again, that's one of those, so it's really theory, very, very new. And, to their credit, they're not rushing to apply this clinically too. They're still saying this has really got a long way to go in terms of making sure that the efficacy is there. But very promising, very interesting.
I think maybe 1 year or 2 years more, maybe the maximum, I think, right?
Yeah.
So, Thelma, can I ask one more question?
Yes, Dr. Mauro Bibancos também fez uma.
Do you wanna ask?
No, say your question.
Okay, he is funny. Okay, let's see. Let's go with my question first, and then I go to Dr. Mauro Bibancos, okay? So, Christine, I was talking about something related to what Thelma said about the andrology lab, but now it's relating to embryologists. So, with the new techniques and artificial intelligence, so we have a lot of technology, a lot of information is being generated, such as the results of the morphokinetics and omics analysis, transcriptomics, metabolomics, proteomics, so of oocytes and embryos. So what will be the future of the embryologist? What with all this data, what are the skills that this professional will need to develop in order to make the best use of this data and improve the results of IVF labs? My question, I'm saying that we have so many information, but if we have information and we don't know how to use the information,
absolutely.
I think what you said before, but now focus on embryologists.
And I think something that it's very tempting, particularly, I'm looking at you and Thelma too. So we're now in the management part, and even in the last 10 years, we've still gone where we've been really heavily on technique based, and we've had to learn why things don't work just as much as why things do work. I think there's a temptation now, perhaps particularly in really busy private practice clinics, where we will train our embryologists purely on the techniques. So we want to, without teaching them the biology behind it. And so I think that that's probably something, again, that's just going to be really important. One of the projects that I'm working on with our research fellows is looking at the whole transcriptome of blastocysts, and then comparing the trifectodome to the inner cell mass. And something that I've noticed, it sort of fascinates me, because I think what you're saying too is, what does it do? What is the biology? We want to know how things work so that we can improve it. But I'm finding there's a whole bunch of, when I'm looking at these genes and I go to look up in, gene bank, they've just been sequenced, but no one has then gone on to say even, what cell types are they expressed in? What do they do? So I think that's fascinating that with the technology, we can almost run crazy and have just a ton of gene names, or even, but we don't even know what are the pathways, what are these genes doing. So that would be kind of the thing that I'm thinking, is that we still are biologists. So we're doing a functional or applied way for our biology. But I think we still must sort of keep doing research, keep teaching the sort of basics of biology and the things that came before, so that we can understand and keep applying sort of the new things.
I think we, like lab directors, we need to encourage the new ones that are coming to the IVF labs to study more, to focus more on the physiology and embryology, not only the technique itself. We need more embryologists instead of technicians, I think that's the point. So, Thelma, Dr. Mauro Vibanco's question, do you want to ask? Otherwise, I have one more question from a person from my team.
Okay. Dr. Mauro Vibanco said, let me find here. Mari, if you don't have the gold standard method to select sperms, what kind of selection have you been using in your lab, especially with high DNA fragmentation?
I think that this is, it is a fascinating problem or issue, because I think that there's been enough information to show us that some sperm, even within, say there's one a semen sample that we know as a whole has high DNA fragmentation. I think as a field, we believe there are some sperm within it that are probably got less DNA fragmentation. And so there is, I think, a value at obtaining or selecting for the sperm that have lower DNA fragmentation. And one method that has been shown, it was sort of done years ago, is just a straight swim up. So there may be some indication that centrifugation may be increasing DNA fragmentation, and then we could be looking at using sperm swim up. That was a fairly recent example that at least was looking at the two different within the same sample, but looking at those that were centrifuged and those that could be just a straight swim up. But other than that, that's it. So it has been the sperm preparation is what we are using in normal spermic samples to hope, because it is sort of a bit of a black box, but we hope that that's moving to select for those with less DNA fragmentation.
Yes.
And again, more studies needed. I mean, I think that's a real issue, but we don't understand it very well at all.
Yes. So swim up is the best at all.
I think that's the
so far, So far.
Yeah, exactly.
Are coming. Okay, Christine, I have a question from Mayara. She is an embryologist from my lab. Okay, she's asking about oocyte morphology. So she's asking, what do you consider that is relevant to choose the oocyte? What kind of abnormality that you not inject one oocyte, or what is a good prognosis for an oocyte relating to morphology?
Right. It's so interesting, and I think in lots of ways we probably don't do a lot of work to try and differentiate that, and it is sort of something that we will inject pretty much everything other than a giant oocyte, so anything that's mature, unless it is the double size ones, because I think there's good evidence that they truly are chromosomally abnormal, so you're not going to be using those. But we tend to be of the plus my lab, we are very heavily using PGTA. Probably 80% of our patients do use that. So we're more of the view that we will use every mature oocyte that we have, rather than selecting those that, say, we think aren't going to do very well. A flip side, I guess, could be the experience that I had when freezing eggs for a donor egg bank. And so with those ones, we really did put a lot of value in the large perivitellin space, so where you feel like the oocyte itself has kind of condensed and shrunken down. Those ones we actually wouldn't freeze. So that actually is a good example of where your oocyte morphology would come into that. The debris within the perivitellin space was something, again, so we would not actually freeze those for the oocyte bank. And we believe that debris is probably granulosa cells, the processes from granulosa cells, but then they've been unhealthy and so undergoing atresia. So those would be the two.
Okay, very interesting. Yeah, I know that a lot of Hienze, from Italy. We studied some articles from her, and she said that like the smooth endothelium aggregates, she doesn't inject those.
That's so
I inject,
interesting.
Yeah, now I'm thinking, should I inject or should I not inject? Because we're in doubt now.
What would be really nice, I think, and valuable is to, and even from, now that you said that, I'm thinking too, go ahead and inject them, because we do want to have the most embryos, but study them, keep them separate.
Good.
and track. And that way, we would think it's like no harm done, because if the embryo arrests at a certain point, we're like, we weren't going to transfer it anyway. But if we've got that knowledge, then that's actually really valuable.
Yeah, especially because some patients, most of the eggs are like that. So what are we going to do, So we don't have the option. That's the problem.
Don't have the option. Yeah.
So, okay, more questions, Thelma?
No, I didn't see
we're
any
okay.
here.
Enough, right? We ask a lot. So, Christine, I'm so happy and glad to have you here today. For me, it was a big pleasure, that, So your lecture was great. Thank you for the answers from our questions. So, and to give us a little bit of your time, to share your experience with us. So another thing, be safe in New York, because I know it's crazy there,
Thank you.
And I think, Thelma, I want to say something.
Yes, I'm glad. Be safe, and thank you for the opportunity to talk to you.
Yeah, I had so much fun. Thank you very much for inviting me.
Thank you very much. Obrigada a todos por terem participado, então, desse nosso primeiro webinar de embriologia. Nós teremos outros aí por vir, né? Obrigada e boa noite a todos.
Boa noite.
Good night, Christine.
Okay,
Good night, Christine.
Bye.
Bye-bye.